Right. Hello and welcome to Algorithms Live. And this week is the start of my Max Flow series. So I'll be covering pretty much every flow algorithm that I know for maximum flows and a few problems that I really like or problem type patterns that I like. And then interspersed with that, there's going to be a few guest episodes. So I've got a few guests lined up, still working out the details. Some of them will be live, some of them will be offline. So just working out those details right now. And so why the flow series? Well, if you saw on the blog, I presented this tidal flow paper at the IOI, and I learned a lot about a bunch of different flow algorithms. I benchmarked them against each other, and I just want to share some of the knowledge that I collected from that paper in a little bit longer flow series and expand upon what I know about flows, because I think there's a lot of really interesting problems using this technique. So why is this episode called Maximum Flow Intuition as opposed to something else? Well, that's when I first started thinking about flows, or when I first learned flows, I found them pretty confusing. I started thinking about things like rates, or I would think about things like liquid moving throughout pipes or something like that. And it just messed with my intuition a little bit. And that's not how I think about flow now. And so we're going to take a somewhat different approach in this episode. I'm going to focus on a problem and just think about maximum flows in the context of this problem, and not use any of the terminology, not use any of the rigor that you typically see in maximum flow. And what will happen next is the next episode will be titled Maximum Flow Formalization. And what this episode will cover is it'll cover rigor, so that way you can understand papers or understand some of the terminology that you can use to understand flow and understand more complicated flow algorithms. But the idea here is to just make an episode where if you've never seen flow before, or you have a lot of trouble understanding it, something that's very intuitive and easy to understand for what's going on in flow and how to implement the most basic algorithm. Okay, so let's start talking about the problem that we're going to be solving with flows. So the input to this problem is going to be three things. So the first thing we're going to have is a directed graph. And then we're going to label two nodes as special. One's going to be labeled as S and one's going to be labeled as T. And so we'll just, I'll introduce one piece of terminology in this, and that is the S node is called the source, the T node is called the sink. And so what would we like to output in this graph? In the problem we're trying to solve is we want to find the maximum number of paths that could be in this graph that go from S to T, and they have no shared edges. So that's the problem we're going to spend today working on, and that's what we're trying to figure out. So we could be thinking about this problem, and we could take one approach is just greedily take the paths. So I'll call that approach one. So let's just run through that here on this graph in the top left and see how that goes. Okay, so what I'll do first is I'm just going to take this path right here, and that's going to be the path that I'm going to find is greedily my first answer. And so I don't discover this path again because I can't share edges. I'll just remove the edges from the graph and try to find another path. Okay, and so now I've removed the edges. I could try finding them below. So we found our second path, we removed the edges, and now we're left with a graph, and all the edges have been removed and nothing has gone wrong. And our answer here is 2. And so that worked out. But it's not always going to work out. So let's look at a case where we end up making a mistake. So let's say our algorithm ends up finding this path instead of the top one on our first go. Then we remove all the edges, it looks like this. And so this is a maximal solution, like you can't add any more paths to it, but it's not the maximum solution. Like it's not the best out of all possible solutions. Instead of just removing the edges, we could try something different. And so the something different is, instead of removing the edges, let's just reverse the edges whenever we find the answer. Okay, so once again, we're going to find this path right here, and let's just reverse the edges that we found. Okay, so what you see here is we've found some path, and then we reverse some edges in the graph, and we end up getting a new graph. And we could just add one as we found one extra path. And so now you'll see we actually have another path that could be found through this graph, and that could be our second path in the graph. But there's kind of this problem here, is this path right here, this blue path that I just found, wasn't a path in the original graph. So what's going on in terms of our solution when we find a path through this changed graph? Okay, so the first thing I'm going to do is I'm just going to remove all of the edges along this path and reverse them as well. And so I get something like this. And if you notice that this edge is once again in its original direction, it flipped. And so you can see that the two paths that we ended up finding, or the two paths that we care about, are this path and this path. And one thing you'll notice, it's almost like I'm taking the first part of this path, and then I've gotten up to where I make this change, and I'm stitching it together with the second part of the other path. So this is forming one of my paths. So I found like the first part of a path, stitch it together with the second part of the path, and then if I look down here from S to T going below, I take the second path, and then this was part of the first path that I found. I'm stitching that together with the path that remained. And so even though the second path wasn't, or neither of the paths was the path I originally found, I am finding the optimal two paths that could go through this graph without sharing an edge. But the thing to think about here is this could be a lot more complex. You could have like several paths, like stitching and unstitching, and it gets really confusing to think about. So let's just come up with like an easier way to think about this in terms of path. So let's look at this path that I've drawn out here. And there's two nodes at the start of the path and the end of the path, and then we have these internal nodes. So we think about properties of a path. Well, the start node has special property. Its out degree is 1. And the end node has a special property. Its in degree is 1, its out degree is 0. And then an internal node has both in degree 1 and out degree 1. Okay, so let's go back to the graph and think about like what happens when one of these edges change. So let's follow our path once again from S to T. Notice that if we reverse something that was an original graph, that's part of our new path. So this edge is going to get reversed, this edge right here, and replaced. This edge in the middle right here was originally the other direction, but now it's been reversed. So we're reversing it back and undoing the decision of it ever existing. So it's actually not going to be one of our path edges, so I can just mark it. We've put it back to original. And then this edge right here on the far side to the right, we can reverse as well, and it's part of a new path. And you can kind of see in the reverse graph, so let's just take only the reverse edges. If we delete everything else, it becomes really obvious what our two paths are, that they don't overlap at all. And the other thing is, if you actually wanted the paths, you just take all these reverse edges and reverse them, and now we have the graph with all the paths. Okay, so let's look at a slightly more convoluted example here. So let's find a path, but let's not pick a pretty good one. So we'll just pick this path here, taking these edges, and then reverse them. Okay, and so that's our first path here. And then we need to find a second path. So perhaps this one, something like that. And you can see when I undid the decision there, I undid the decision on this edge, we end up having two paths still that are disjoint. They get stitched together, One thing you can be realizing here is if you only look at the red edges, look at those internal nodes. The internal node has one leaving on the reverse edge and one coming in on the reverse edge. So that property is being maintained every time we find one of these new paths through this new graph that we formed. And so let's do this again and find another path. So the last path that exists is this one, this, and then this. And so if I just remove all the edges that aren't the reversed edges, you'll notice that the sum of the incoming edges always equals the sum of the outcoming edges. And it's not always one. Remember, it's edge distinct paths. So this is 2 coming in, but there's always incoming and outgoing that are the same. And we can actually find the paths. So if we took the reverse of this entire graph, there's never really a decision of consequence anymore. Like I could take this path, or I could take this path, and if I wanted to extract the edge distinct paths, I could just take any path through this graph. It's not going to affect a future path from being found of the 3 paths that we're trying to form. So I could just find this path, remove it, then find this top path, remove it, and then find this bottom path, remove it. And those are the 3 paths in my answer. So this is just kind of a nice property of just thinking of it in terms of paths. I think it's fairly intuitive, just thinking about flows this way. Okay, so let's talk about parallel edges. So what we could have here is we could have several edges going forward instead of just one edge going forward, leaving a node. So these are called parallel edges. And there's a pretty simple way we could handle this here. We could just keep a number, just keep a count for this edge, how many edges are going in this direction. And we get something like this. So this is just labeling how many edges are going forward. And so we can just draw a whole graph out this way. Instead of having a bunch of edges, we just keep a number of the edges going in that direction. And yeah, so we could have a graph like this, and instead of having a bunch of edges, it's got these numbers. And so how do we handle edge reversals? Well, we just put another edge in the opposite direction that tells you how many edges are going in that direction. And so initially they're all 0, so it doesn't really matter. And so I'm just going to run through a quick example of finding augmenting paths, and you can just think through this. So what we can do is we can find one path. So there's a path from S to T along the top here. So I'll just take that one. And what you'll see is I'll just remove one from this edge, and this edge, and then replace it in the graph. And it's basically doing the same thing as the edge reversal technique. It's just doing it on these values. So let's find another path through here. Let's go down and then through the middle and then over to the right. So we'll change it here. And so that's what's left there. And so now I need to find another path. Well, I can't go this way because that's 0. I can see the 2, but I can't go this way anymore. So maybe I'll come down here on the bottom. So just this bottom path here, send one path down this path and see how that goes. And now you'll see that there's no longer any path that I can find from the start to the end. And so I could pull out the answer, and the answer would just be this path here. Yeah, so there will be 3 paths. So it's this path up top, this path through the middle, and then this path through the bottom. So you kind of have to keep track of like where your reverse values were for this to work, but that's one way you could get this answer out. So the last thing I'm going to say is why only find one path? We could actually find a couple paths down this path. There's actually 2, because you see there's multiple edges here. So if we just find the edge on our path that has the smallest value, we can just subtract that amount from all of them and update the path accordingly. Something like this. And that's all it is to do max flow. So this algorithm of finding these paths this way is called Ford-Fulkerson. And how do you find a path? Well, we already know this, it's just depth first search. So we could use it to just find any path that we care about. So what I'm going to do is I'm actually going to go ahead and implement this and just show you one way of coding this algorithm now that we've just like talked about how this works and some thinking about it. Okay, so let's talk about the code I have here. So I've already put in a little bit of the code just reading an input. So the way these files are structured, it's the first 4 numbers are the number of nodes, number of edges, the source node, and the sink node. And I have a test suite of tests that I'm going to run on this that were generated in this style to test to make sure my MaxFlow code is working. So hopefully I'm just implementing this correctly. And I've created a solver class, so I usually call this MaxFlow, but I'm just calling it solver here. You can look, pretty much all the flow code I'll be writing in this series is going to be in this format. So it just has an add edge function. It takes in the first node, second node, and tells you how many edges are between them. We usually call this a capacity, and that's what I'll use here. And then I have this run function that runs MaxFlow, distorts the graph the way I described. And then the last thing it does is it just returns the value of the flow. So let's get started. I'm actually going to use an adjacency matrix representation here for the, we'll call them capacities, but the values on the edges, telling us how many edges are going down some direction. And I need to do a breadth first search, so let's just keep a scene array. So I'll just do scene and capacity. And since this is Java, this will fill it all in with zeros. Okay, so let's talk about our add edge function. So this is an adjacency matrix, pretty simple. I just increase the number of nodes going down this edge. And I also need to increase the reverse by 0, so I don't really need to do anything. So this code just becomes this. All right, so let's imagine we have depth first search. So I'm just going to write the method signature. So I'm doing a depth first search. This is keeping track of the smallest edge I've found so far, this amount value. This is my target, so it usually just comes in as the sink. Yeah, I guess I don't even need to pass this through as a parameter, so I'll just keep track of till I find the sink. And this is the node I'm currently on in my depth first search. So let's just write, let's just assume this piece is working and then go down to the run function and see how you can use it. So this is my run function. So I need to keep track of the total flow I've sent through the graph so far. And I also could keep track of the last amount that I sent last turn. So I can write this as a handy while loop. And so I just set it as -1, so my while loop could kick off. I could change this to a do while as well, but this is convenient to write as well. I'm doing a depth first search, so my scene has to be empty. And then I do my DFS, start from my source, and I just imagine that I'm able to send as much flow as I can possibly. And this will get constrained by the edges. Sometimes you might want to put a smaller value if you're worried about overflow or infinity values. That's something to worry about in problems with really large capacities. So something to think about. Add this to my total, and it'll kick out of this for loop as soon as it doesn't find any more flow to send through. Like it can't find any edge. And then I just return the max flow. What was the total that it was able to send through the graph? So the last thing I need to do is code this DFS. So my base case is I'm at the sink. Well, it's just the amount of flow that I'm sending is the amount of flow that reached me. So I constrain every single edge by this capacity and get out to this particular point. And let's loop through all our neighbors. And this is how you do that if you don't have an adjacency list. So yeah, make sure we have a capacity and make sure we haven't seen this node already. Could do something like this. So I need to take the min of the amount that's reached me so far and the edge that I'm currently considering. So I to j, and that's the amount sent. And if I'm able to send more flow than 0, then I've managed to find an answer. So then just return what I've sent. And then if I couldn't find any paths, then just return 0, because I couldn't find any paths from this node. If I've already reached my base case, then as I'm coming back on the recursive stack, I never have to, I'm only going to be hitting edges that are coming off the stack one by one. So it's only going to be edges on the path. And those are the edges I want to switch directions. And so you'll hear this term augment in terms of augmenting paths. So when I cover in the next episode terminology, that's a term, is augment this edge. And so that's what I'm doing here. I'm just taking this capacity and I subtract out the flow I sent. Remember, you reverse all the edges coming out. And then in the opposite direction, there are more reverse edges. So that all this is doing is just reversing the direction that I can send flow. Yeah, and that should be the flow algorithm. So it's pretty simple. It's just a DFS with this small piece where I think about, oh, I need to change the graph every time I find a path that can go from the source to the sink. Yeah, pretty short code. And pretty intuitive. The algorithms get a lot more complicated later on for flow, and I'm certainly going to be covering a lot of crazy ones. Let's compile this, make sure it compiles. Oh yeah, I need... That would have worked in C++, right? Make sure I can send flow down that. So let's make sure it works on the samples. So it works on the samples. So I'm just going to run my test script and this will take a while. All right, so my algorithm finished. You can see on some of these tougher tests, it takes pretty long. And so this would be TLE on pretty much any reasonable problem. Yeah, that's the future episodes are going to be about how can we make this algorithm faster? What are the different flow algorithms that are fast enough to solve for competitive programming? So thanks for watching, everybody, and I'll see you next episode.